Hi, my name is Paritosh Mokhasi. I'm a kernel developer at Wolfram Research, and today I'll be talking about linear and quadratic convex optimization models. So Rob mentioned that he gave the overview of convex optimization. I'm going to focus on linear and quadratic optimization models. So just to give you guys an overview, or rather a reminder of what convex optimization is, you're basically minimizing a certain function subject to a certain constraint. And what makes it convex is that it satisfies this certain inequality. Okay, I won't. Rob showed a couple of graphics, about how a function is convex, based on this inequality. But let's just focus on this part and see what forms these functions f take to be classified under either linear or quadratic models. So if I were to, is this big enough for the people in the back to see? Yes? Okay. Yeah, somebody says go up. All right. If the objective function, so f naught, is linear and the constraints are also linear, then it's considered a linear optimization problem. If the objective function is the ratio of two linear functions, then that becomes a linear fractional optimization. If your objective function has this form, which is a quadratic form where Q is a matrix, then it becomes a quadratic optimization problem. And if your objective function is linear, but your constraints have this norm in them, then that's the second order cone optimization. Okay, and it's not hard to see that the second order cone is sort of the most general one, but like linear optimization is like a subset of quadratic and second order, and the other ones also can be converted into other ones. So, so linear and quadratic themselves they encompass a very large set of models, but you can extend that models by doing these transformations. And Rob showed a number of these transformations. These are some of the popular transformations. So if you ever open up a book on optimization, and you're interested in doing some practical modeling, you're bound to come up, run into these kind of transformations. So if you want to do some kind of a norm 1 optimization, you can convert that into, using some transformations, you can convert that into a linear optimization model. Same thing with an infinity norm. If you want to do some infinity norm minimization, same thing. You convert them, that it gets transformed into a set of linear constraints. Rob showed an example of absolute x. Here's a nice fancy way that you can represent absolute value of x using two auxiliary variables. If you want to convert a set of linear functions and you want to find the maximum of that, then again you have these transformations. So using these transformations, you can extend the scope of linear and quadratic optimization models. That's the point I'm trying to make here. So let's jump into linear optimization model. So the syntax that we have in Mathematica is linear optimization. It'll have an objective, which is a symbolic objective. You'll have constraints, and then you'll have variables. But we also allow you to directly give vectors and matrices, vector objectives and matrix constraints in order to solve the problem directly. If you are getting confused as to why are we calling stuff optimization, linear programming is what it was called before. And we had a function called linear programming for a very long time, and we still do in Mathematica. Optimization is just like it's like a more 90s name, because we lost rights to programming in the optimization community, and so that's why we have linear optimization now. But under the hood, linear optimization is basically making use of the same functions and the libraries to solve the problem. Now I want to go back for just a minute, because that's sort of the whole point as to how you properly give the inputs into into these optimization functions that make it obvious and easy to use. And Rob spent a good amount of time talking about all these vector inequalities and this modeling paradigm that you could use to your benefit. So there are the obvious ways that you can give an input. So let's take this specific example. You want to minimize x plus y subject to some constraint. The most obvious way to do that is to give it in a symbolic form. This is and then just run it. Or you can convert this into matrix vectors and matrices. So the x plus y is 1, 1, right? And then these constraints can be mapped into this a matrix and a vector, and you can give that as an input. It's not the most intuitive one. You have to do a little bit of mental calculation, but if this becomes really helpful, for example, if you import a data from some external source wherein they might have it in this matrix vector form. So we provide that capability for you. But the most important thing, especially from a modeling point of view, is that you can use these vector variables. So again, you can use these coefficients and just dot them with a vector variable v, and the internal parsing system recognizes that v is a vector. It's got a certain dimension, and it just goes ahead and solves the problem for you, right? You can use vector greater equal or vector less equal, which allows you to group a number of constraints all into one, and that's a real that makes life a lot simpler. And you can use this escape notation, and Rob quickly alluded to that. You can use this escape. So let's try that here. Escape v greater equal escape, and that brings that little squiggly, rather this curvy inequality thing into place. And when you do that, the thing starts becoming smaller and smaller. So again, linear optimization, same thing happens. Or you could use this parameter equations, right? And again, same. It's a question of convenience and what works best. Sometimes, and I'll show you examples wherein using matrix vector forms seems to be the most efficient way to represent a problem, just obvious. And in some cases, using symbolic methods are just the more obvious choice. So let's look at linear optimization examples. The very first one I'm going to tackle is data fitting, because that's sort of very ubiquitous. We're going to focus on robust data fitting, which is minimizing using the L1 norm. And I talked about the L1 norm and the transformations you can do with that. So here's the raw data. It's noisy data. I'm going to fit a curve through it. I'm going to use this multi-quadratic basis functions, and then you'll end up with this interpolating function. So objective here is to try and find these lambdas. Okay. So that's your basis. I'm going to use 10 of them spread at equal intervals. I'm going to use design matrix to generate an input. So this is going to be a matrix. Then I'm going to solve this L1 norm problem. So this input is your A here, okay, and B is your output. So A is the input, B is the output. That's the transformation that takes place, and you're trying to minimize the total of S. How about that? Didn't I? Something changed, didn't it? Interesting. Well, try it 100 times before, and now it decides to. There we go. All right, so that's your lambda, and that's your S, and of course you can plot it, and that's your result. It's as simple as that, right? So you can see that the modeling allows you to, the actual problem solving happens in rather just one line. And if you just look at it long enough, you can actually read the problem statement directly from the code if need be. Here's a second example, which is a classification problem. You have two sets of data, and you just want to separate these two sets of data, and you want to find like a line that separates these two sets, right? So the way you would do that is you want the first set to obey this constraint that, you know, the line on one side should be greater than or equal to 1, on the other it should be less than or equal to -1. So that gives a good separation between these two sets of points. Notice that there is no objective because technically this is all a constraint. So go ahead and find any line that you want as long as it gives us a good separation. So we solve this problem. We get A and B, which are the coefficients associated with the hyperplane, and that's your line, right? So it separates one from the other. I mean, you could change this to, I don't know, B. B is a scalar, and it changes a little bit, and that'll change that line angle a little bit. So you can play around with it. It's a lot more intuitive. It allows for more exploration if need be. Okay, so linear fractional optimization. This is this is taking a step from linear optimization. The main thing is that you have this denominator sitting here. So the syntax is identical in all of these functions, which I've labeled out here. Now, if you want to give it in the matrix vector form, then you give it, you give this alpha, beta, gamma, delta, which has these vectors and scalars, and it goes ahead and solves this. Now, this linear fractional problem actually can be transformed into a linear optimization problem. So we can use the exact same solvers that linear optimization uses to solve linear fractional problems. And the way you do that is using this transformation called Chance-Cooper transformation, which is this transformation right here. And when you apply this transformation, you get this equivalent optimization problem. So the interesting thing about linear fractional optimization is where it's essentially used. You'll typically encounter optimization problems wherein you want to minimize and maximize multiple objective functions. You want to minimize cost, maximize profit, and you want to do that simultaneously. Linear fractional optimization allows you to do that. So that's one way to do it. There are other ways to do it, but linear fractional optimization would be one approach that you could use to solve these kind of multi-objective problems. One thing I do want to point out, for those who start using this, is that because there is a denominator, there's a very good chance that this denominator could go to 0, which means that inside this conic the region, you could end up getting singular results. But that's the objective function goes to negative infinity, but you'll still get the value of x and z will still be something finite. So that's something to keep in mind. Okay, so best way to talk about linear fractional optimization is through an application problem. Okay, so I'm going to talk about the transportation problem. It's a toy problem, but I'm sure it'll convey the underlying message. So what we have is we have a transportation company. It wants to transport 5 goods from point A to point B, and there are various costs associated with it. Okay, so the cost of transporting these 5 goods per unit is 100 across the board, but the profit that they make is different. So cost per unit, profit per unit is given to us. Okay, now associated with each one of these units, you have a weight, right? So each product weighs a certain amount, and there is a maximum number of units that the transportation company can transport. And so that's weight per unit and max units that it can transport. Now the company will have some kind of a minimum operating cost. They own trucks, there's fuel cost, there's labor cost, something to that effect. So that's like that standard cost is 2,000 in this case, and the additional cost comes with whatever goods that they're transporting. So 2,000 plus cost per unit dot x, and this is where we introduce our first variable x. So x becomes is a vector of 5 which basically represents the number of units you're going to use, which you're going to transport. So that's your cost. And the truck makes a profit, a minimum profit. If you use the truck company, you need to pay $1,000 upfront. So even if it rides empty, it's going to make a profit of 1,000. but then additional profit is made by basically how much profit by transporting the goods. The truck obviously has carrying capacity of 8,000 pounds, so you can't go above that, and it can't go negative in terms of carrying the goods. So these are obvious, or rather in the literature they would be called natural constraints, right? So weight constraint and goods constraint. And now that you have set up the problem, the problem that you're trying to solve is you want to minimize the cost, maximize the profit. Okay, that's also called efficiency in some jargon. So cost divided by profit is what you're trying to minimize. You have weight constraint, you have goods constraint, and you have a vector. You solve the problem, and there you have it. And it says that the truck will make its most profit by just transporting the first, third, and the fourth product with that number. So this should give you an idea. And when you look at the documentation of this, you'll notice that this is how we set up the problem, so that it's quite easy to follow through. Okay, quadratic optimization. Again, just for the objective function is going to be quadratic with linear equality constraints. We also allow, if for the quadratic optimization case, we also allow you to give what are called as factored forms. And factored forms turn out to be really important, or really useful rather, in data fitting kinds of problems. Okay, I'll skip directly to the examples so that you can see what we're talking about. Again, I'm going to talk about the data fitting problem, but now it's just a basic norm fitting, right? This is exactly the same example. I'm going to use the same basis and do the interpolation. But now notice that instead of giving the result, or rather the input in the symbolic form, I'm giving it in a matrix vector form, because it's just obvious to give it in this form. You give the A and B are just directly known to us. This A and B is directly known to us. So rather than introducing new symbolic variables which make no sense, let's just directly give those give those inputs, matrix vector inputs, and that's your result, and that's your fit. Okay, so again, it just works seamlessly. Internally, it's using there are multiple solvers that you can invoke. There is the coin library that you can use, or you can convert this problem into a conic optimization problem, and you can use the conic solvers, the dedicated conic solvers, to solve that. Okay. All right. A second example is geometry. When you're talking about quadratic problems and norms, this idea of distance and it becomes almost comes naturally in these kind of formulations. So in this example, I have two regions, two polyhedras, and I want to find the minimum distance between those two polyhedras. And so x1 is a point that is on region 1. x2 is a point that belongs to region 2. I want to find the minimum distance between those two, and that's the formulation. So you can find the minimum value, and primal minimizer rule basically gives you the x1 and x2. So that's the first point, that's the second point. Okay? And this is the minimum distance between the two. And there you have it. Okay? All right? So now the thing that is often overlooked is the dual. Dual is a very, very powerful thing. If it takes a little while, it takes a little bit of time to getting used to dual concepts, but once you do, you realize that it's really powerful. And I want to explain the idea of dual using the specific example. We have this region, and we want to find the smallest ball that encloses this region. And you can't. So that's the objective. That's the optimization problem you want to solve. Minimize R subject to a number of points that are less than or equal to R, and you want to find this R and C naught, the center of the circle, of the ball. But this is not a quadratic optimization problem. This actually is a second-order cone problem. But as it turns out, that this problem's dual is actually a quadratic optimization problem. So this is the dual of, this dual formulation allows you to solve this problem as a quadratic optimization problem. So the W now turned out to be weights, so the center becomes the weighted sum of all the points that you have, right? So that's the objective. You go ahead and get the weights. That's your center, which is weights, and the radius becomes the square root of the negative of the minimum value. And the negative is because dual is associated with maximizing an objective. If your primal is minimizing, then your dual is maximizing. Okay, and so that's your radius, and then you can visualize this. And there you have it. Now, I do want to point out that just because the dual is available and you can do it, it's not always a good idea. What I'm trying to say is, this is not the most efficient way to solve this particular problem, because this scales linearly with the number of points, and it's just not as efficient. You'd get a much faster and more accurate result using second-order cone optimization. But you should know that the dual does have a lot of good properties that you can use to your benefit. Okay, I'm running a little short, so I'm going to jump to second-order cone optimization, which is basically minimize. Its objective function is linear, but its constraints have this norm in it. Okay. Jump to an example. This is basically you're trying to find a disk, the distance between two disks that are separated, and so you have two disks, and you want to find 2 points, one on each disk, and you want to find the minimum distance between those. And those are the 2 disks, and those are the 2 points. The graphics makes it much easier to tell the story. And you can find the distance between those two directly from the result, or you can compute it yourself. They're going to be the same. Okay. I'm going to skip this example because I really want to talk about sensitivity analysis while I have. So and I want to talk about it in terms of an example. Let's say that you have a company that's manufacturing 3 products, but it uses 4 machines to do that, and that's the distribution, and it has a number of constraints that you can't run the machine for a certain number of times. You have a maximum capacity on the products and what have you. So you set up the constraints, and then you solve the problem, and then you say that okay, the profit that I get for this problem of manufacturing these 3 products is 7,600, whatever. But the real question and the power of sensitivity analysis comes in is, what can I do? How can I analyze this problem so I can increase my profit? Okay, what can I do there? And that's where sensitivity analysis comes on its own. You can extract the constraint sensitivity, which is just a vector of numbers, and you'll notice that some of these sensitivities have 0. What that 0 means is that the constraints that belong to these 0 elements don't have any effect on your bottom line, on your profit. So you can change them in whatever way you want, but your profit's not going to change. On the other hand, you have 3 constraints that if you do make any changes to them, you should see an increase or decrease in profit. So that tells you that, so that's your analysis tool right there. So let's extract the ones that give you a direct effect on the profit. And you'll see that the first one, it says that if your increase x3 should be greater than or equal to 60, it means that the third product, the maximum I can produce is 60. If I increase that second product to producing 70, I should see an increase in profit. So max 1 I get, and max 0 was this. So I do get an increase in profit. If I don't change that, if I increase 1 or 2, right, I see no change in profit. So rather than running these examples over and over again, you can use sensitivity analysis to your advantage to do really useful analysis. Okay, I'm way over time, so I'm gonna stop now, and I'm gonna take any questions and enjoy this plot. Questions?